Okay, so I'm going to be talking about a new LM fine-tuning technique that I've developed, as well as kind of like giving an update on it. I wrote an article about this a while ago, and I recently started doing some initial training with some pretty good results. And I think that it kind of divulges a bit from what I've seen other uh, reasoning fine-tuning do, and perhaps there are reasons why there are people that aren't doing what I'm doing. Maybe it's not the best, but I guess we'll see. Um, there are definitely some shortcomings in my method, but there are also plenty of positives. So this is kind of like this article I wrote a while ago. But right now, most of the LM fine tuning that you're seeing when it comes to chain of thought LLMs, reasoning LLMs, is some kind of thing of either PPO, SFT, or the new kid on the block, GRPO, which is a variation of PPO, as is, I would suppose, my new LM fine tuning technique. But what is the kind of so whenever we have a chain of thought LLM, we have some sort of question, right? Our question that is asked to the user. We have some sort of chain of thought, right? And then we have an answer associated with it, right? Our answer. So what are the kind of shortcomings, and of SFT, right? SFT just trains a model on how to sound like a chain of thought thinking chatbot. So SFT is something we can go ahead and just kind of discount pretty early. And even with GRPO, it's not even like we necessarily have to do SFT. SFT is good for our initial cold start, potentially, but it's not going to get us the results that we want. DPO is not really, it's kind of part of PPO, though when it comes to chain of thought LLMs, not really. It seems like they use more rule and pattern matching methods for the reward function and not DPO models, not reward models. So PPO is still used quite a bit. There are issues with PPO, right? One of the ones being is that PPO rewards are sparse. They're sparse in the sense that, we have a question, we have our chain of thought, so our this is masked, the chain of thought and the answer. PPO, for the advantage term, will provide a single score, right? So, -2 or +4, whatever, right? And it will provide it for this entire chain of thought and answer. And it leads to potentially some very noisy updates. But more importantly, as this chain of thought grows, you have a single scalar value, and it doesn't really kind of teach the policy model what you're actually supposed to be learning, right? So PPO is a very it's not a very precise tool. You have sparse rewards coming from the reward model, or in what we're seeing now with GRPO and new PPO methods, they're using stuff what I like to call pattern matching, right? Pattern matching is just kind of like you have math, and you can do some sort of some regex matching. For coding, we have some unit tests. And these are all kind of like our ways of essentially taking what the LLM does, which is abstract text, right? It's text content, and turning it into a numerical value or score, because we've already determined that DPO reward models do a pretty bad job of doing this, right? So, this kind of gets us into what this chain of thought fine-tuning technique is. So just like most models, we did do an SFT, kind of like initial step, but this is where we start to get into more of the actual data, kind of like the data heuristics about chain of thought, right? So first off, whenever we're trying to have a chain of thought model solve a question, at the very least, what we typically have is we have the question, right? So for PPO, we'll have the question that's going to ask, the policy model will generate an answer, and then we'll do the whole KO divergence thing. We'll have a reward model. And we may also have for GRPO, we may have an answer, right? But in my RFT approach, we actually have for a given question, we will have a rubric / answer. And what this rubric / answer is done is it is essentially a, like, in my RFT method, the actual reward function is another LLM, another smart LLM, like a GPT-4o or a llama 7 billion, llama 13 billion, something like that. It's not just like your typical reward model. It's an actual another LLM. But the other LLM is given asymmetric data, right? So the other LLM is actually given the rubric and the answer, right? So we have like a policy model, and the next slide is actually going to show what this looks like, right? So we have this smart LLM, we have this like asymmetry. So this is like the perfect example, right? We have a question asked our reusing LLM, our policy model, and it is going to generate a chain of thought, right? So this is like, Sarah had $50. She bought a book for $15 and then a toy for $10. After that, she earned $25 from a part-time job. How much money does Sarah have? Well, Sarah had $50 initially. She had to spend a book. Then she saved 20% on car insurance, something like that, right? She's $40. And I purposely made this wrong. But we have like in this thing, we have our policy model, and we have our grader. Our grader is another smart LLM. I just put an OpenAI logo, but in reality, this can be GPT-4o, Azure mode, so that way no licensing issues. Or this could be llama, something else like that. But the point being is that it's actually given a rubric, right? And this kind of goes back into general data heuristics, where if we have LLMs we've already determined, I think many people determined that they're okay at solving math. They're not that perfect, right? But for any question, right, inherently speaking, even from a human perspective, if you give me a rubric to grade a potential solution, I can do a better job of that than trying to solve a question, right? So it'll be harder for me to actually solve this question than it will be if I get a potential solution, I have a rubric that has this kind of level of granularity, and for me to score it is not too difficult. And this is what we're kind of exploiting here. So, and the other thing is that each chain of thought is actually given its own score. And we have methods for fine-tuning with that, and we're going to go into that. But the whole idea is that this was good. This was good. This was good. This is good. This was horrible, right? This was not what we needed. This threw off our answer, and this should be scored negatively, right? And the model should learn, and if we had a PPO method, what it would do is it basically just scores this entire thing negative, which is not what we want to do. This may work in smaller and kind of like the initial stages of training of post SFT, because we have so many data pairs and whatnot, and this one chain of thought thing ruined the entire batch. But as we keep converging, we're going to start to get into more of these niche cases where we really do need to go in the per chain of thought link, as I call it, a chain link level rewards. So like this is kind of what this somewhat looks like, right? Is that it learns that, this is like our mask. Everything above this is our mask. So these won't be considered in the reward, but like take, for example, given this state, right, we generated this, this is our score. And we do this for all n chain links within the chain of thought. So it kind of learns, okay, I start off with this question. This is a good start. Then, I start off with this state. Okay, this was good. I start off with this state. This was good. Keep going, and then it kind of learns, okay, if I've generated these chains of thought, if I'm going like this, generating this is bad. And that is the granularity that chain of thought RFT really does present, right? We kind of have that level of granularity. So this is kind of different in the sense that it has, and here's some benefits, right? Over the whole thing. So number one is that we don't need to worry about pattern matching, as I call it. Pattern matching is essentially like, we have a code deterministic way of proving if an answer is right or wrong, right? For coding tasks, this is unit tests. For math, this is string matching for the correct answer. But this inherently limits the domains in which we can train reasoning models. If the answer can't be, expressed in a few characters or as something that's like verifiable in a code sense, like, unit tests, then it's hard for us to actually fine tune in those categories. I'll also be sharing a data set I made called Open Mystery, which was distilled from like cop crime TV shows, and I used Claude to go ahead in the API, and it split it into like I basically told it to take a transcript from a NCIS TV show, summarize it, and then break it down into a start state and a rubric/answer. And the idea is that a murder mystery or something like that isn't really something that can be verified by code. But another LLM using a rubric can do that. So that's kind of a use case where our current methodologies of how gRPO works won't work in that context, right? And this is kind of where I get into at the time of writing this article, which was back in December, I thought I could get rid of KO divergence. For reference, this is a diagram of PPO. Ish. No, not really. This is mine. Notice here you don't have KO divergence. I've since added this back. I think that it helps with numerical stability, though it does increase training cost. But this is kind of like a alteration of PPO, right? And the main thing kind of being is this whole grader reward model, which is different than the PPO usage of reward models, which was, basically just takes in the same data. So it's kind of hard also for LLMs to try to reward hack these models, just because, GPT-4o and other smart LLMs aren't very easily hackable. Okay. Yeah, so here we're going to start to get into the actual meat and bones of RFT, right? So I kind of talked for a while, giving you some background, but now we're going to actually get into this, right? This is a different alteration of the same question, but this is one generated by DeepSeek. This is the 1.5 billion parameter fine tune. I can't write to save my life. And yeah, this is a rubric that was LLM generated from the correct answer, right? So it generated an answer key or a rubric that will go ahead and score a potential output, right? So if it's proficient, exemplary, all these kinds of things. So what we will do is that we'll kind of like take this thinking tags. We'll split up all the text, and notice whenever it comes to these chains of thought that it always has a particular delimiter. I default it to just like 2 new lines, right? And what I'll do is that I'll actually break up the chain of thought into chain links, right? So this is what happens, right? We get these chain links, and the LLM is fed this, and it's fed like a function call, right? And it's just told, okay, give this score. And this is also something that I've recently worked on. That is a alteration of what I discussed earlier. And that is correctness and incorrectness highlighting, right? Basically, what it's just going to go ahead and do is it's going to go ahead and like within each chain of thought, it's going to go ahead and figure out how to distribute rewards or how to potentially even add rewards just based on like, okay, like which parts of each chain of thought were good, which parts of it were bad, and we're just asking the LLM like generate like lists of substrings within each chain of thought. So yeah, we kind of yell at it. This is kind of like where we have prompt engineering kind of meeting the ML training side. So like this is kind of like what we're going to get from the response critic or from the critic LLM. we get back like the score, we'll get back this correctness highlighting, this is the text that was associated with it, same thing here, so on and so forth, and yeah, so this is kind of like how it would look like for PPO, right? We have like this single sparse reward, it would be, maybe +2 or something like that, probably not positive since we got this one wrong. Or actually, probably still positive since we got it right, even though our chain of thought was completely incorrect, right? So this is a perfect example of why PPO can fail. It is giving positive reward, even though it kind of just was lucky with this last part. In reality, the math it did here was incorrect, right? But this is what it looks like in the kind of like earlier part where I was just talking about doing per chain of thought rewards, right? So Sarah had $50. These kind of green highlights represent rewards. This is kind of like yellow because there's some part of it that's right, or not right, but gets it back on the track, and then there's some part of it that's very clearly wrong. And here's what it looks like with token highlighting, right? So we have, even within each chain of thought, we have different token distributions. And for actually calculating the rewards, so the LLM will also generate a overall score for the actual question, right? So final answer, it'll generate the final score. So the way in which we go ahead and match it, right? The way we're going to go ahead and match it, I'm going to try to skip past some of this complex math, but it's essentially going to be, we're going to adjust each one of these chains of thought by essentially having our base overall score that's going to apply to all of these. And then we're going to go ahead and add on to it for each chain of thought. We're going to go ahead and figure out, okay, let HI plus be the set of positive highlights, HI negative be the negative set, and we're going to iterate through all of these, and we're going to multiply these scores, and we're going to essentially redistribute the rewards. And yeah, this is somewhat a very glossing over of the math involved with this. I think the actual math is a little bit more complex than it needs to be, but this was the simplest I could represent it as. And this is where the actual token level rewards are a little bit finicky, since the way in which it's trained isn't exactly per token. I initially decided to do per token rewards, and I've since backtracked on this. And I will get into why I backtracked on it. But this is kind of our final expression for expressing our reward functions. And here we kind of have like, this is our incorrectness highlighting. So this is our incorrect answers. Correct answers, this is our correct answers, and we're adding them together along with SI of n, which we can represent as being, SI of n is our base score, n of I, base score, and this is our per chain of thought score. So you can kind of see we have multiple layers of rewards. So there is also a repetition penalty that I didn't get into, but essentially this is kind of a thing where LLMs can kind of reward hack, where at least that I found it in my initial training of the model, where essentially it would just keep generating long chains of text, and it would just like start repeating itself and whatnot. And the way to fix it is that there was a small reward I'd apply, like that did grow semi-exponentially based on the number of chains of thought or chain links in the chain of thought, because we do want to make sure that doesn't reason too much. So yeah, we've talked about the token level rewards. So yeah, these are token level rewards. Okay, so let's talk about the actual. Okay, so this is our actual RFT So this is where we can get a little bit crazy, but if we're going to go through it, essentially we have here, we're going to go ahead and, so, with GRPO coming out, it seems like value heads are disappearing from PPO. I have included a value head, and I've run some experiments. Value head is a good idea. The reason why it is because we can kind of append onto the chains of thought that came to it previously. So the value head can actually very much stabilize our numerical. It can give us a lot of numerical stability, even more so than compared to PPO. Since PPO, we kind of just have a question answer single turn style questions, whereas value term we have like multiple, like chains of thought. But in general, what kind of like the thing that we have here is, let's define M. I believe we define M as our, right. So let's first get into some of the definitions. Pi theta is our policy model. Pi ref is our reference model. The main one being is that M is the number of chain links that we have within our training thing. So if we go back to like this example, we're going to iterate over 1, 2, 3, 4, 4 chains of thought, and we will kind of, like the visual example showed from earlier, we will essentially do something like this, where our value head, by the way, gets this, and we'll go ahead and this is our state, and it's going to predict what the reward will be for the new text that we've generated, so on and so forth. And this is kind of the way that the training loop goes. So each question we will actually call loss.backwards on each chain link. So that is computationally pretty expensive, but I have seen it produce some pretty good results. And even you can call the optimizer.step on it, though I wouldn't recommend it, especially for multi-GPU setups. Second. There we go, scrolling. Okay, that also works. Yeah, let's go into the actual complex parts of chain of thought fine tuning. Right, so here we have our advantage term. Our advantage term is essentially just like, previously we talked about the rewards that we get at, chain link I. So this is just that's just that reward minus the value head of the, current state, the value head's prediction. Additionally, we also have some clipping that we also do to ensure that numerical stability doesn't blow up, as well as KL divergence, right? KL divergence is also to make sure that our we don't divulge too much from our policy model. And basically, for every single question, we iterate over M chains of thought, and N is so this is like our chain links, CLs, and these are our tokens within each CL. So tokens within a CL, and basically, right now it technically is a per token loss, but the actual code implementation, I have changed it to not be per token. I mentioned that earlier, and the reason why is just that per token losses cause the model to converge too slowly. So we have sparse rewards. I've reintroduced to that, but it is only per chain link, so it is still better than PPO. Though yes, the per token losses have proven to not help the model converge so quickly, even though they actually were very numerically stable as far as like the model never gave any absurd output. But yeah, so this is our number of chain links, so we'll iterate over all of our chain links, as well as all the tokens, and we're going to go ahead and choose the minimum of our reward, our advantage term, as well as like the clipped advantage term, minus the value heads term, and all of that minus the KL divergence. And that will kind of give us a way of like the difference I want to drive home that we're doing differently with PPO is that we are taking into consideration the actual data heuristics of reasoning LLMs. And that is kind of the point that I'm trying to drive home. And within these reasoning LLMs, they can oftentimes generate like a single, a few words within a single chain link that derails the whole chain of thought. And we're getting around that. And I'm going to make a follow-up video where I do this even a little bit more polished. And I even show more code as well as actual results. But I'm really excited about this, and I'm really looking forward to being able to spin up a bunch of GPUs and be able to see how this performs, because right now I've just done some initial small experiments. That being said, I really do think that the whole data kind of thing of having a rubric does change the paradigm a bit, where rubrics kind of act like a way to make a reward function. And I think you can synthetically generate rubrics so long as you have like a question and the correct answer. You can tell an LLM to break apart the question, the correct answer, and create a rubric and kind of create this asymmetric data flow. And I think like one of the benefits that I guess I want to like quickly talk on before I wrap this up is that, like, take for example like even encoding, right? DeepSeek and whatnot, they use like unit tests, but there are cases in which you want code but it doesn't have to work, right? So like think about more like design docs and more abstract code, right? Code for projects that are much larger and more agentic tasks. These are cases in which using unit tests won't work, but that will also cause GRPO and other kind of unit test based reward functions to not work. But if you give an LLM, like a commit, right? So like a perfect example is that if you give it a commit from an already, fulfilled Jira ticket, and you try to get that LLM reference agent to go ahead, or the policy model to try to go ahead and fulfill that Jira ticket, right? That already been completed. The critic model, you can go ahead and create a rubric based on that already closed issue. So in reality, the actual amount of data you have for training is, think about how many Git repos there are, how many Jira tickets. It can be quite endless. But anyways, I'm going to go and wrap this up. This has kind of been a very hacky video. Not as polished as I would have wanted, but just an update on this LLM fine-tuning. And yeah, I hope to give an update in the future where I can kind of go over some more results.